As heat is added to a beaker of water, the vapor pressure of the water increases, thereby increasing the rate of evaporation. If enough heat is added, the vapor pressure of the water equals the atmospheric pressure. At this point, large bubbles of vapor begin to form in the liquid, and the liquid boils.
Vapor pressure, like all pressures, go up with temperature. So we saw in the gas section, PV equals nRT. Pressure and temperature are proportional. So temperature goes up, your pressure goes up. And this applies to vapor pressure as well. If the vapor pressure equals the atmospheric pressure, which for 1 atmosphere is 760 millimeters of mercury, when vapor pressure and atmospheric pressure are the same, this is when a liquid boils. So you start seeing liquids boil when the atmospheric pressure and the vapor pressure of the liquid are the same. And this is kind of an interesting process. So maybe you've heard that at some cities you have to boil things longer, all right, if they're higher elevation, like Denver, Colorado, for example. Well, this is why. The pressure, the atmospheric pressure at Denver is less than 1 atmosphere. So it boils quicker. You're trying to get heat to the food or whatever, so it takes a little extra energy. So boiling, we can actually talk about what boiling is. Boiling is where the vapor pressure of the liquid equals the atmospheric pressure. And that's kind of interesting, as you're going to see here in a little bit.
In the flask is water heated to about 55 degrees Celsius, well below water's normal boiling point. We use a device to evacuate the air from the flask. The water boils, though its temperature remains at around 55 degrees.
Water boils at 100 degrees Celsius normally, all right? But let's say you wanted to make water boil at, in this case, 55 degrees Celsius. You can do that by lowering the external pressure, because remember that boiling is when the vapor pressure equals the atmospheric pressure. So if you lower the atmospheric pressure, it takes less vapor pressure to reach it, and it's going to boil faster. So water can boil 55 degrees Celsius, 65, whatever you want, if you play with the atmospheric pressure. So this is an interesting thing. The normal boiling point for a compound is when it boils at 1 atmosphere of pressure. But you can have boiling points at all different values if you change the external pressure. In my world of chemistry, if I wanted to get rid of the extra solvent, sometimes I could lower the pressure, the solvent would boil off without hurting my compound. It was a really nice kind of purification technique, but there's lots of other uses for it too, as you can see.
Heating the liquid water converts it to a gas, which pushes molecules of air out of the container. The inverted can traps the gaseous H2O when we place the can in cold water. The temperature change converts the gaseous water into liquid water, which occupies a much smaller volume. The can is crushed by the pressure of the atmosphere.
This is kind of a cool chemistry demonstration you can do at your house if this is anything you're interested in. But anyway, what they did is they took an empty aluminum can and they put a little bit of water in it, all right? And then they heated the water. In this case, it was over a Bunsen burner. And so what happened is the liquid water in the can became a gas. And the gas occupied the entire volume of the can, all right? Well, then what they did is they took the can with the gaseous boiling water, fumes inside it, and they inverted it and put it in cold water. So what that did is it shocked the system. The gas molecules turned quickly into a liquid, and liquids don't have the pressure associated with it. So liquids go down to almost nothing. The external pressure just crushed the can like that, and you get some pretty interesting kind of results, as you can see. So yeah, so if you turn a liquid into a gas, the gas takes up all of the volume. But then if you can somehow turn the gas back into a liquid, the volume goes way, way down. There's no more pressure pushing back, and the outside pressures, which are around us all the time on the Earth, crush the can. This has huge implications. These are actually big train cars, all right, that were quote unquote empty with just a little bit of some kind of substance in them. And what happened is maybe on a hot day or whatever, someone thought, oh, I'll clean these cars and make them look pretty. Well, as you clean them with probably cold water, the cold water made the gas inside condense down, just like we saw in the can a little bit ago, and squish, everything was crushed. So I can imagine there were a lot of bad words said those days. Just be aware. You should be very careful if you have to clean the cars and stuff. Make sure you don't do them on the wrong kind of day. Don't crush your train cars. This is a graph that shows the vapor pressure for 3 different substances at different temperatures. And you can see that on the left is diethyl ether, the middle one is ethanol, an alcohol, and the right one there is water. Now, at the top, in this little line right here, the dotted line, those are the normal boiling points of those compounds. So the normal boiling point is where the substance boils if you're about at 1 atmosphere of pressure. But you can also see the different vapor pressure curves. And notice their curves, all right? They're going slowly up there. The vapor pressures are increasing with temperature. And also you can see the difference here in the intermolecular forces. So let's think here about the intermolecular forces. Diethyl ether has an oxygen connected to carbons. Oxygens usually have 2 lone pairs on them. So diethyl ether is polar. It doesn't have hydrogen bonding though, because the oxygen isn't connected to a hydrogen. So we would classify diethyl ether as dipole-dipole. Both ethanol and water have OHs, and that's one of the magic hydrogen bonding combinations. But water is extra special here because water has 2 OH bonds. So you can imagine that water has like 2 sources of hydrogen bonding possible, while ethanol has just 1. So here, water is actually the smallest grams per mole of all these compounds, but it has the higher boiling point because in theory it has twice the hydrogen bonding of ethanol. Pretty interesting. These curves, the red curve, green curve, and blue curve, they are vapor pressure curves, and they show all conditions of pressure and temperature where the liquid and vapor are in equilibrium, all right? So the vapor pressure is rising with temperature, all right, because pressure and temperature are proportional, and remember, vapor pressure is a pressure of a gas. When the vapor pressure equals the external pressure, that's when you can have boiling. And at 1 atmosphere of pressure, you can see like diethyl ether boils at 34.6. But if you wanted diethyl ether to boil at 0 degrees Celsius, in theory you could do that. You would have a vapor pressure just under 200 millimeters of mercury, and you should be able to make it boil. So you can change the boiling points of all these things by changing the external pressure. When the external pressure is 1 atmosphere, which is 760 millimeters of mercury, the temperature that it boils then is called the normal boiling point. And most of the time when you hear people talk about boiling points, they're normal boiling points, i.e. what is it at 1 atmosphere of pressure. And you can see that the boiling points are increasing based on their intermolecular forces, like we talked about. The intermolecular forces go from dipole-dipole, which is the diethyl ether, to a hydrogen bond on the ethanol, to multiple hydrogen bonds in water. So the intermolecular forces are certainly playing a factor when it comes to the boiling points, just like we've seen with all the other things so far. These intermolecular forces hold on to the other molecules stronger, so it takes a little bit extra energy to make them boil. So on the basis of the relative strengths of the intermolecular forces, the predicted order of decreasing boiling points for the following substances is, and there's 3 substances here we're looking at. The first one is methanol, which is another type of alcohol, but with a methyl group on it. We also have methane, CH4, and we have hydrogen, H2, all right? Now, we want the order of decreasing boiling points. So we want the highest boiling point first and the smallest boiling point last. Well, you can probably see that methanol, CH3OH, has a hydrogen bond, and that's going to be stronger than the other two, which don't have hydrogen bonds. So I'm going to predict that since we want strongest to weakest, all right, or highest boiling points to weakest boiling points, methanol should be the first one because it's got the strongest intermolecular forces. It's going to be more like ethanol in that graph up there. CH4 and H2 are both non-polar. CH4, if you draw out the Lewis structure, is a carbon in a tetrahedral form with hydrogens all around. So it's symmetric, it's non-polar, and H2 is literally two hydrogens together. That's also non-polar. So both CH4 and H2 exhibit induced dipole forces. So if they're the same force, then we look at the molar mass, like which one is heavier, which one is lighter. Because remember, boiling is kind of like pushing something into the air, and lighter things are easier to push into the air than heavier things. So I would look at the molar masses of CH4 and H2. So CH4, carbon is 12 grams per mole in the periodic table. Hydrogen's about 1, and there's 4 of them. So that would be 16 grams per mole for methanol. Hydrogen, 1 gram per mole hydrogen is about 2. So methane, CH4, is heavier. So I would predict that methanol, again, is the heaviest. The next one would be methane. And finally, hydrogen would be the last one. So answer A here would be what I would go for. And again, we used intermolecular forces to first pull methanol away from CH4 and hydrogen. After that, since CH4 and hydrogen were the same induced dipole force, we would then look at the molar mass to see which one was heavier.